Hi, good morning. Hope you all had a good breakfast. Okay, so today I'm going to tell you about local search. So local search is another technique for designing approximation algorithms. You've seen some techniques already. Um, and this is actually one of the simplest techniques, algorithmically one of the simplest things. It becomes sometimes challenging to analyze it, or sometimes one cannot prove any worst case guarantees with this technique, but still it's quite useful in practice, right? Of course, the problems I'm going to consider today are those for which we can analyze the quality of the solution that this technique provides and claim bounds. So what's local search? So let's do an example, right? I'll take the example of max cut. Have you already seen the max cut problem and the SDP for it?
Yes,
Everything, including local search? No.
not local search. Everything except local search.
Except local search. Okay. So you all know that. Okay. So what's the max cut problem? You have a graph, and you have let's just say no weights on the edges, so unweighted graph, and you want to find a partition which is a cut, and max means that you want to maximize the number of edges between the two sides of the partition, right? As complement, and you want to maximize this. Right? So what would be a very simple algorithm for doing this? You start with some solution, and you take a vertex, let's say here, and you ask yourself, if I were to move this vertex from here to here, will the size of the cut increase? And if it increases, then you make the change. Right? As simple as that. Okay? So when will it increase? It will increase if the number of edges that I have here is more than, if it is less than the number of edges I have here. Right? The blue is less than the red. Why? Because right now this vertex is contributing 3 edges in here, right, into the cut. And when I move it across, then it is going to contribute 4 edges to the cut. Yeah? So if this blue is less than the red, then I would move it across. Conversely, I would not move it across if this is more, the blue is more than the red. Right? Then I will not move it across. So that's the entire algorithm actually. Right? So you take any vertex from any side and you ask yourself, if I move this across, will the cut increase? If it does, you make the move. If it does not, you don't stop. You don't consider that vertex. You consider every other vertex, no improvement, then the algorithm terminates. Yeah, so I can write the entire algorithm, repeat, check if there exists a vertex which, when moved to other side, increases size of cut. Right? I'm writing it in English, but you can translate it into more formal notation and make the move. Repeat until no improvement possible. Yeah. Okay, just so that we all understand what this algorithm is doing, who can tell me what the running time of this algorithm will be? Linear. Okay, let's break it down into two steps, into two arguments. First, what is the running time for one iteration? Right, in one iteration we would be checking various vertices and seeing whether that will increase. And then let's count how many iterations there will be. So first, how much time will I spend in an iteration? Degree of the vertex, right? Why? Because for every vertex, I will have to check what is its degree on the within the side that it is on, and what's its degree on the other side, right? And I guess you can keep some appropriate data structure so that this can be done in linear time. So each iteration would be linear time, but how many iterations would there be? Huh?
Number of edges.
Number of edges at most. Why? Because that's the size of the largest cut possible, right? With every iteration, the size of the cut is increasing by at least a 1. Yes? Because I'm making the move only when the size of the cut increases. So with every iteration, it's increasing by at least a 1. The number of, the size of the largest cut is m, the number of edges in the graph, so there are at most m iterations, only less than that. Yes? So yeah, so m times m squared roughly would be the running time of this algorithm. How would one analyze it, right? I'm going to write a set of inequalities, right? So what are the set of inequalities I'm going to write? So I'm going to say for all, okay, not a good color, for all vi belonging to S is this side, degree of vi in S, so let me say at local optimality. So what is a locally optimum solution? A solution which cannot be improved, right? And let's say the solution S comma x complement is locally optimum. Up, I cannot make any change. So if I take any vertex vi here, right, what can I say? The degree of vi in S is how many edges vi has on this side. And the degree of vi in S complement is how many edges it has going across. Which of these two is larger if this is a locally optimum solution? That is larger? Yes? Why? Because there are more edges going across than there are within, right? So if there were more edges within, then I would have taken it on the other side. Yeah? Okay? Let me sum up all of these inequalities. I can write this inequality for every vertex in S. I can also write this inequality for every vertex in S complement. Yes? Degree of Vj, so if Vj is a vertex here, degree of vertex Vj in S complement here, within here, the red edges, is less than the degree in S, which is the blue edges. Now let me sum all of these inequalities for all vertices in S. If I add this, what am I going to get? What will the left hand side be? Degree of all vertices Vi in S. Twice the number of edges in S. 2 times the number of edges in S. Let's say E of S denotes the number of edges within S, or the set of edges within S. So 2 times the size of this. What's this going to be? Size of the cut. Everyone sees that? Right? Because for every vertex here, I'm looking at what its degree is there. So it's exactly the size of the cut. So SS complement is the cut, size of the cut is that. Yeah? What about this? When I sum this up, what do I get on the left? 2 times number of edges in S complement now. This is less than the size of the cut S complement. Yeah? Nothing very sophisticated, we're just summing up some inequalities. Now let's sum up both of these. So what do I get? 2 times the number of edges in S plus the number of edges in S complement is less than 2 times the size of the cut SS complement. Okay. Let's get rid of the 2's. So what do we see? Size of the cut SS complement is larger than the number of edges here and the number of edges here. Yes? So let's add SS complement to both sides. The size of the cut SS complement. Why did I do that? Because this thing now is all the edges of the graph. This is n. And this is 2 times the size of the cut SS complement. So the size of the cut SS complement is at least m by 2. And this is definitely more than optimum by 2. Why? Because optimum cannot be more than the total number of edges in the graph. Yeah? Simple? So this gives us a half approximation to the optimum. In fact, for a very long time, maybe 20 years, 25, 30 years, this was the best approximation known for max cut till Michel Giemans and Williamson came up with the STP algorithm that you've seen in an earlier lecture. So trivial algorithm really. Very versatile still, right? So if I say find the largest balanced cut. Okay, what do I mean by balanced cut? The number of vertices on both sides are equal, right? Suppose I asked you to do that. What do you think would be the local search move now you will make?
We'll compare one vertex on both sides.
Sorry?
We'll check one vertex on the left side and one on the right side.
And? So we'll start with a solution which is balanced, right? Equal number of vertices on both sides. And now we'll see if we can improve it, right? But I can't just take one vertex and move it to the other side. So I should be swapping, right? Take one vertex from here, one vertex from here, and see if swapping them improves. So I'll look at all possible n by 2 squared options, and if any one of them improves, I'll make that move, right? So this is not on your tutorial sheet, but think about what would be the guarantee that you can give for this algorithm, right? In the exercise sheets, I've given a question where you want to maximize the largest directed cut, okay? Where now edges have directions, and you are, let's say, trying to maximize the number of edges going from the S side to S complement. Right? But for all of these, you can use a simple local search algorithm. Okay? So now, अगर ये सब समझ में आ गया, so let's do another problem जो इतनी आसान नहीं होगी. Why will it always terminate? Yeah, good question. Why will this always terminate?
Increase it.
We are only increasing the size of the cut at every step, right? The maximum that we can have is m, so there can be at most m steps. There are no weights on the edges here.
But after a vertex moves, will it not happen that other things have also moved, so it needs to come back?
Yeah. So our vertex might move here, and then it might come back here, and then it might come back here, and a lot of this can happen. That's okay. But I don't care about that. I'm just looking at the size of the cut as my potential function. That's only increasing every step. Yeah, it's never decreasing. And it can go from 1 or 0 to capital M, sorry, M the number of edges, so at most M steps. Okay. So now, let me give you something more non-trivial. going to talk about the K-median problem. Okay? And many of you might have also heard of what's called the K-means problem. Okay? Have you heard of K-means? So it gets used a lot in, it's become very popular because of machine learning, right? And there's K-means is a clustering algorithm. Yeah? So K-median is something similar. We'll talk about K-median, but whatever I'm saying, a lot of it can apply to K-means also. So let me tell you what the K-median problem is. So I give you a set of points. So it's a clustering problem, right? So I'm drawing points in the plane, but this could just be a graph, right? The vertices of a graph. And I have a distance metric. So n points or clients. D is, so V is a set of n points. D is from V cross V to non-negative reals. Right, so what that means is basically that I give you the distance between every pair of points, and its distance, which basically means it satisfies triangle inequality. Yes? Or the metric property. And now I want to open some K medians, some K points I want to identify. Maybe this, maybe this, maybe this. Let's say K is 4, so maybe this. And such that the distance of every point from the nearest median, right? So think of these as some facilities you have opened. Maybe you're a bank manager, you have money to open 4 ATMs, right? And these are the locations of your clients. And now you want to open your ATMs in such a manner, such that your clients are served, that for every client, you know, there is a ATM that's close by, right? So, and the metric you're going to work with is the total distance your clients have to travel to get to the nearest ATM, right? There is no reason why someone will go to an ATM which is further away than the closest one, right? So each one of them is traveling to the closest ATM. Maybe this guy goes there, this is closer, this, that. Okay, no, maybe this one. This looks closer to me. Maybe this guy goes there, this goes there. Yeah, maybe this is how the clients traveled to the closest ATM. So what is it that I'm trying to minimize? I'm trying to minimize, so okay, so open K facilities to such that distance of every client or sum of distances of clients to nearest open facility is minimized. Okay, everyone understands the question? The problem, this problem statement. So you're given the set of points in the plane, you want to find K is given to you, the fixed number. Says that the sum of these distances is as small as possible. K means is the same problem, but instead of sum of distances, you are doing sum of. Someone know what happens in K means? You're doing sum of distance squared. Okay? Instead of distances, you're doing sum of squares of distances. That's the only difference. So if I wanted to write it formally, I could write it as, so let me define d, j, comma, s as distance of j from nearest point in S. What is S? S is a subset of V. Right? So that's fairly standard. So if I give you a set S and I say I take J, then D or J of S is the distance of जो भी point closest है. Right? And so with this terminology, this objective becomes I want to find minimize over all choices of S, subset of V, size of S is K, right? So I'm finding out which is the set of points to open, such that what's the objective? D, J, comma S. So S is such that this is the distance of J from S, and this summed over all J belonging to V. So that's just a formal way of saying what I wrote there in words. So that's what you want to do. Now, what do you think should be a local search algorithm for this?
Any random K points.
Pick random K points, okay? Then what? You have to tell me where the local search is.
Then try to replace one of the K points with another point if not that.
Yeah, okay. And when will you replace?
The
If
sum
the-
decreases.
If the sum decreases. Yeah. Yeah. The algorithms are always very simple. Right? This is the analysis which will make you sweat very soon. Okay, so what's the local search algorithm? Repeat. Okay, so let me define a swap. And okay. Repeat. If there exists J not in S, such that S cost of S minus. Okay, sorry. If there exists I in S and J not in S, such that S minus I plus J, cost of this is less than cost of S, then what? S is set to S minus I plus J. Repeat until no improvement in cost. What is C of S? What is C of S? Cost of the set S. What's the cost of the set S? This quantity. Yeah. So if I have a set of facilities, I'll call the cost of that set as what's the sum of the distances of all the points to this set. And I want a set with the minimum cost. And what's that algorithm doing? It's saying अगर कोई एक point है अंदर I और set S के अंदर एक point I है, there is a point I inside S, a point J outside S, such that by swapping them, I can get a smaller cost. So S minus I plus J. I'm removing I is inside the set S, right? I'm removing I from S and adding J to S. If the new cost, or if the cost of this new set is smaller than the cost of the current set, then do the change. Yes.
Are there any variant of this problem like wherein your distance is at most k and you want to like minimize the number of points where you want to have the facilities?
Minimize the number of points. Okay. So everyone should be served within a distance of k, and you want to minimize the points. Yeah, there are lots and lots of variants of this problem, right? So facility location is a domain where there are hundreds of researchers working in this domain and multiple books and so on. Okay. So what problem you are talking of is what's called disk coverage, right? So suppose I give you a set of points, abhi plane mein socho, right? And I say you want to cover all of these points by disks of radius. What distance do you want? K or R, let's call it. Right, I'm using K for numbers, so let's call the radius of the disk as R. So now I want to cover all of these points by placing disks of radius R. That's exactly your problem. And I want to use the minimum number of disks. Right? You could say, okay, I fix the number of disks, but I want the radius to be as small as possible. So I want only K disks, but I want the smallest possible disks of radius R, which will cover all the points. That's called the K center problem. Okay. I already told you what the K means problem. There are many facility location problems. Here I told you how many centers you want to open. But suppose I don't tell you how many centers you want to open, but there is a cost opening with each center. Cost of opening each center. Right? So like you would imagine in a facility location setting, if I set up a ATM here, maybe it costs 10 lakh rupees. If I set up an ATM there, maybe it costs 5 lakh rupees. Maybe you want to open an ATM in UB city, it costs 1 crore city rupees or whatever, right? Location, cost will be different depending upon location, right? And now you want to, you can open as many as you want, but now you want to minimize the total cost of opening plus the cost of serving. Yes? So this is what we call the service cost as well, this sum. Okay? And then there are many variants. Here, you know, you can talk of, okay, you don't want, you know, this facility serving only one client and this serving so many clients. So you want to, maybe you want to place a capacity on how many clients a particular facility can serve. So that's called the capacitated facility location problem, right? And for all of these, actually especially the capacitated ones, the best algorithm known are local search algorithms. For this K-median problem, the best algorithm, I'm going to show you an algorithm which is going to be a 5 approximation, but this is not the best approximation known. So there are other algorithms based on linear programming rounding which will give you better than this, but this is still one of the easiest algorithms, right? You guys came up with the algorithm yourself. The analysis is going to be slightly more hard, but these are very simple algorithms to state and implement, for instance. Okay?
Is the problem change a lot if the points are not really the points that we need to choose among the points?
Sorry?
Will the problem change a lot if the points that we want to choose are one among the points?
Or not amongst the points, it doesn't change too much. So you can identify a separate set of points and you call them facility locations, and you say you only have to open here. It will not change a lot. But one thing you should be wondering here, or one of you asked that question, why does this terminate in polynomial time? Earlier, we said it terminates in polynomial time because at every step things are increasing by at least a 1, and it can go up to m, and so at most m steps. Now, here will things increase by at least a 1? No. These distances are reals, so your cost might increase by just a tiny epsilon.
Total possible distances are n squared.
Sorry?
Total possible distances are
N squared, but we are not looking at number of possible distances, we are looking at sums of distances, and the sums of distances can be much larger, right? The different possible sums, and that would be a much larger sum. Okay? So we use a simple trick. We say we make a small modification. We say we will make this only if this is significantly smaller, right? Or maybe I'll write it as times 1 minus epsilon. Maybe think of epsilon as 0.1. So what does that mean? It says that, well, it's not just that the new cost is less than the old cost. It's, let's say, 90% of the older cost or lesser than that. 0.9 times the older cost or lesser than that. So there is actually a significant improvement we are talking of. Yes? So for instance, if I said if it's at most half the old cost, then you can see that with every step I'm halving the older cost, right? And this cannot happen too often, right? If the original cost was something and the final cost is, the optimum cost is something, I can only halve things logarithmically many times. Right? Even with this, because I'm doing a multiplicative decrease, it will be logarithmic still. Maybe not log base 2, but maybe log base 0.1 in this setting or something like that. Right? So I'm not going to spend more time on this, but you can make it polynomial time by introducing such an idea. Right? That, and this is fairly standard again, right? That you don't say, because just saying improvement in cost means the improvement can be very, very tiny, right? And then you will not be able to argue polynomiality.
You can actually come up with bad examples.
Sorry?
You can actually come up with bad examples for if you don't do this trick.
Where it will take,
Super polynomials.
I've not seen one myself, but I imagine it should be a way of doing it.
And you also do
It's just that the number of steps will be very large. It will still terminate,
sure.
but it will, the number
I'm
of
not
steps,
like you will not have a polynomial problem.
you will not have.
And also you're not particular about making like a greedy choice. You're not picking necessarily the best
No,
pair. An arbitrary pair just as long as
Exactly.
it meets the
Again, there are variants of this local. So this is like a vanilla algorithm, right? I mean, these are really 2 lines only, right? Then there will be variants where you could say, okay, you look at all possible pairs and you see which is the best improvement, and you do that improvement, right? Or you could say, okay, you pick a random pair and use that. And all of these have been used in different settings, right? So this is a very, just a basic algorithm, and you can add some bells and whistles and make it more interesting.
So, just confirming, the final approximation I get, will it depend on epsilon?
Yes, to the following extent. So I'm going to show that this algorithm is a 5 approximation. So cost of S is less than or equal to 5 times cost of O. I'm going to reserve O for optimum solution, right? So this is what I'm going to show here. And if you have this, then it will become 5 times 1 plus epsilon times cost of O. Okay? So it will worsen, the approximation guarantee will worsen by a factor of 1 plus epsilon. Okay, so how are we going to do this? So I'm going to draw my clients. So these are my clients, or essentially, I do not formally say what clients are, basically all the endpoints that we have, right? So these are my clients. These are my optimum facilities. Let's say there are case 4. So remember, and these are my facilities in my solution. So this is S. So S I'm going to use for locally optimum solution. So I've ran that algorithm. I got a locally optimum solution, right? Just as for the max cut case, now I need to put together a set of inequalities to argue कि ये जो locally optimum solution है, this locally optimum solution, how bad is it compared to the optimum solution? Okay, and the way you should think of this is that this client is served by that, maybe. Right? There's no particular ordering on these clients. So, maybe this distance from here to here is smaller than this, so I would have drawn that line. So, but just to keep the picture neat, I've just drawn it in this line. Right? So this is maybe. I could do with a bit. maybe this is what my own solution looks like. So the cost of my solution is the sum of these blue lines, yeah, sum of the distances corresponding to these pairs, and the cost of the optimum solution is the red, the lengths of those red lines. So remember, what is our step? We are at some point shutting down one of the facilities, right, and opening one of the facilities which are not in my solution, right? And I'm trying out everything possible, right? So which means that I would have shut this down and tried opening maybe this facility, right? And it did not give me an improvement. I tried shutting this and opening this, and that did not give me an improvement either. And I tried shutting this and improving this, including this, and that did not give me an improvement either. So I tried shutting this and opening in all of any one of these, and none of them gave me an improvement. And ditto for this, and ditto for this, and so on. Right? That's what a locally optimum solution is. Any pair did not give me an improvement. Okay, so what I'm going to think of is that I shut one of these facilities. So I'm going to identify certain swaps. So analysis, idea, identify a set of we're using I, j swaps. So remember I belonging to S, J belongs to S complement. So we're going to identify a certain set of swaps. Okay. And then we are going to write the inequalities corresponding to those swaps. Okay. So what am I going to do? I'm going to make a simplifying assumption for this class. So let me take a facility J belonging to the optimum solution, and let me look at the clients it serves. So we'll call this, okay, let me write it in English and not introduce most clients served by J in O. Right? So for instance, ये जो facility है optimum solution में, this is serving 4 clients. So this I would have drawn a set of 4 clients here, and so on and on. Okay. So what am I saying? The set of clients that are served by, I took a facility in the optimum solution. I looked at the set of clients it serves, and I'm now going to partition this set based on which clients were served by which facility in my solution. My solution is the solution S, right? So maybe all of these 4 clients were served by a facility using I, so maybe they were served by a facility I1 in my solution, right? And these 4 clients were served by a facility I2 in my solution, and this one client was served by I3 in my solution, and this one client was served by I4 in my solution, and these 2 clients were served by I5 in my solution. Yeah, I can always do that. Look at this set and look at, so for instance, if I've been looking at this facility, this is the 2 clients it is serving. One of them is served by this facility in my solution, one of them is served by this facility in my solution. And the simplifying assumption I'm going to make is that, okay, none of these pieces is more than half the total size. Okay? क्यों? अभी समझ में आएगा. So assume for all I belonging to j belonging to O, n O j intersection n s I, इसका size is less than half of n. Abhi I'll explain the terminology in 1 second. N O J. Okay, what is N O? N O, we are using J, is set of clients served by J in O. ऑप्टिमम सोल्यूशन में अगर ये J है तो ये किस सेट ऑफ क्लाइंट को सर्व कर रहा है, तो N J O is going to be this, and similarly N S and subscript SI equals set of clients served by I in S. So I'm also using that S there in this way, so there is no confusion. So what is this saying? The intersection, right? So in any case, this is just NOJ. This set is just NOJ in my notation, right? And this set is not all of NSI, right? Because ये जो एक particular I है, ये I1. So this is a part of that, right? This is the intersection part. क्योंकि यहाँ की एक facility कुछ यहाँ से के clients का serve कर रही हो सकती है, कुछ यहाँ के serve कर रही हो सकती है. But each of these parts is less than half. Okay, क्यों कर रहा हूँ मैं ये सब? अब मैं क्या करूँगा कि मैं इन clients के बीच में एक mapping बनाऊँगा. I'll make a mapping between the clients. Says that every client is mapped to another client which is not in the same set of this partition. That's the only requirement. Okay? कैसे भी वो कर लेते हैं, इसको इसके साथ मैप कर लेते हैं, and अभी symmetric mapping बनाएंगे, and this requirement will ensure that this mapping is always possible. Okay? इसको इसके साथ मैप कर दिया, इसको इसके साथ कर दिया, इसको इसके साथ कर दिया. अब I have to be careful, right? ये इसके साथ कर सकता हूँ, ये इसके साथ. Right? Take my word for it, it can always be done. अगर कोई piece जो है आधे से बड़ा होता तो कर सकते हो, राइट? उसके क्लाइंट्स बाहर मैप होने हैं और वो खुद आधे से बड़ा है तो कैसे हो सकता है? तो दैट्स व्हाई दैट कंडीशन. या इफ एवरी पीस इज लेस देन हाफ द थिंग, देन इट कैन ऑलवेज बी डन. इट्स नॉट रॉकेट साइंस. लेट्स अज्यूम इट कैन बी डन. नाउ व्हाट एम आई गोइंग टू डू विद दिस मैपिंग? क्यों बनाई है आपने? अब मैं क्या करूँगा,
और इसका कोई ऑड इवन का चक्कर नहीं है.
इसमें ऑड इवन का कोई चक्कर नहीं. Whether it is even or it is odd, oh, you're saying the total size has to be even. Okay. Actually, मैंने यहाँ पे इसको symmetric बनाया, but I could also have made it asymmetric. And even then it would be fine. तो अभी just to simplify matters, we kept it symmetric. तो वैसे ही रखते हैं अभी, but odd even का भी कोई चक्कर नहीं है. ठीक है? It will not make a difference. Because if it is odd, I can always do something like that. But I want to show you how this mapping is getting used. Yeah? Okay, so let's say I'm writing an inequality corresponding to, I see, remember I said I'll identify a certain set of swaps. Suppose मेरा swap में ये मेरा I है और ये मेरा J है, मैं इन दोनों को swap करना चाह रहा हूँ. इसके लिए inequality लिखना चाह रहा हूँ. Yeah. Oh, sorry. You, thanks for interrupting me. Yeah, I will try to. So I'm trying to do this swap between I and J. Right? What's the problem? Right? When I close I and I'm including J, right? So first I have to identify, when I close I, all these clients which were getting served by I in my solution, where are they going to go? Yes? In this case, suppose I decided to close I and open J, what can I do? What should I do? Tell me. What should I do? The clients, 5 clients are served by this I. I am opening this facility, right? So where should these 5 clients go?
So first 4 will be served by J. And
The first 4 should be served by J. Yeah? Why can I use J? Because I am opening J.
and
The 5th guy,
will be
what happens to the 5th guy?
served by some blue vertices.
It has to be served by some blue vertex. It cannot be served by this one because this is closed. So it has to be served by some blue vertex. Which blue vertex should it be served by? Huh?
The nearest, the next nearest one.
The nearest one. We could do it that way, yes. I'm going to use a slightly more sophisticated thingy here. I'm going to say, well, I mapped this to some other facility using this mapping. To some other client using this mapping, sorry. Right? Which could I have mapped it to? In this example, it's actually very trivial because this would be one set corresponding to this, in which this lies. Yes? Remember, when I drew this ball for this particular facility, these are the only 2 guys in there, and this would then have to be mapped to this one. So this was mapped to this in this mapping. So when I have to serve this, I'm going to send it to whoever is taking care of this one, which is this. So this guy is going to go to, this guy is going to go to here. Okay, we'll do one or two more examples so that it becomes clearer. So I'm saying if I'm going to shut this, these 4 guys are going to be, if I'm going to shut this and open that, yeah. If I'm going to shut this and open that, then
Does this diagram make sense? Because you said that the intersection is less than half of.
yeah.
The rate to work.
Yeah, coming to it. Right? So if I shut this and open that, then I'm good. Right? All of these 4 guys can go there. This 5th guy can be served by whoever is serving its mate in the mapping. And its mate in the mapping is this guy is serving it, so he'll go there.
So
Yeah.
just one question. In order to find the mate in the mapping,
Yeah.
do I need the knowledge of NOJ and therefore O?
Of course, to find the mate. But this is all a mind game. Your algorithm is done and cooked. This is just analysis.
Okay.
This is just to have fun with you guys, nothing else. The algorithm is done. Right? We're just doing the analysis. And for the analysis, I can assume I know O and S in the world, right? So that's. But yes, very valid question there. Okay, so what her question was, and I'll show you now. Okay, so suppose let's take a different one. Okay, let's think of this swap. I and J. No. I and okay, I and J ये ले लेते हैं. So if I close this and I open that, what am I going to do? If I close this, these 2 clients have to be taken care of. This will go there because I opened this. This will go to whoever its mate is, and because these 2 guys are the only ones together in a ball, this mates will be this. So this will go. What color did I have to use? Okay, so this is mapped to that in my mapping. I know that, and so this will be served by that. Okay. Now.
So when you are closing I and opening J,
Yeah.
the last 3 vertices you are saying that optimally served by J.
This one is served by J.
Yeah. So how
This
do-
one, these 2 are still served by my own facility.
Sorry, this one.
Yeah.
So but how are you sure that this is the nearest? J is the nearest to this.
Good point. Very good point. We'll come to all of that, right? So we are designing a way of assigning clients to facilities. We are designing a way of assigning clients. This need not be the best, that's what you're saying. right? There might be an even better way of doing things. But even if the best way of doing things is not improving cost, then my way of doing things, which is not the best, cannot be improving the cost either. So I'll just write an inequality saying my way of doing things, which is not the best way, is not going to improve the cost because this is a locally optimum solution. Right? Too many words, but don't worry about it. So just for now think that I'm going to pick up some swaps and say, okay, you go there, you go there, you go there. I decide who goes where. And I'm going to say this way of assignment is not improving the cost of the solution, which means the new cost of the solution, the cost of the new solution, is larger than the cost of the old solution. So I'm going to write those inequalities. And what he's saying is, your way of doing it is not the best possible, but the inequality will still hold because even the best possible was not improving cost. So how can something which is less than the best possible or worse than the best possible be improving cost? Yeah? Okay. Good. So you must be wondering कि मैं fraud मार रहा हूँ, and I am. So suppose I did I and J here, right? Suppose I decided to swap these. Now I'm closing this, all these 5 are be served. What happens now? This can be served by this guy. But who's going to take care of these? They are served by him. Right? But there is no mapping here. Why is there no mapping here? Because this ball, more than half of this ball, so if I think of this n ball corresponding to this facility, more than half of this is served by one guy. Yeah? So actually this example of mine is not consistent with my assumption. We can make it consistent with my assumption by taking 2 or 3 things away from here. I can say this is served by that, and
I think the red one is the optimum solution.
sorry?
The red one is the optimum solution.
The red is optimum.
We should be changing the blue edges.
No, it doesn't matter. I can change anything, just. Yeah? So the red is the optimum solution, the blue is my solution. And if this were the picture,
I think she might be saying that this NO of J for now, that leftmost 2 guys are the intersection is
their intersection is, yeah. Yeah, okay. Okay, maybe I can't build an example right now which sort of meets that my constraint, but we will have this constraint, right? And now let's just write the inequalities, right? So if I have this assumption, this simplifying assumption, then I can actually swap anyone with anyone. Okay? Why can I swap anyone with anyone? So the way I'm going to think of it is, this is my i's in my solution, right? These are the climbs served by I. Right? These are the blue edges. These are served by I in my solution. I'm shutting I down and I'm opening a J which is in the optimum. Right? And this J maybe serves something here, maybe it doesn't. If it serves here something here, fine. If it doesn't, that's also fine. But all of these guys are served by someone else, right? Maybe these 2 are served by the same, maybe these 2 are served by the same, maybe this is served by someone else. Yeah, this is what the picture will look like. And then we are going to look at, right, because, you know, this ball will have to have at least 2 more people, right? And similarly, this ball needs to have at least 2 more people, and this needs to have at least 1. And I'm going to show the mapping in green now. Maybe this is mapped here and this is mapped here. Maybe this is mapped here and this is mapped here. And maybe this is mapped here. And so now, again blue, because I'm going to look at where they are getting served. Maybe this is getting served by these facilities and this facility here, right? They are getting served by different facilities in my solution, right? This, and this. So what am I going to do? Right? Looking complex, but you understand the idea, right? I have to take care of these black guys. These, because I opened this facility, these can be taken care of by that. It's the others I'm worried about, and they will go to wherever their mates are going, whoever is serving their mates, and their mates are given by these green lines, right? This guy has this as its mate, it is served by this one, so he is going to go here. So I'm going to use a blue dash to do this. And this guy is served, this guy is served by that. Oh no, this is wrong. So this mate is this, so this is going to go there. And this guy is mated to that, so this guy is going to serve there. So we took care of these two. This is mated to that, so he's going to go there. This is mated to that, so he's going to go there. Right? There are 3, right? So this also is mated to that, so he's going to go there. Okay? Now let's see. So if I write the inequality corresponding to this assignment, what will I see? I'll see, so what is the cost of the dashed lines? Right, the cost of this dashed line, for instance, now here I'm going to use triangle inequality. Right, the cost of this dashed line is at most this cost plus this cost plus this cost. Right, so I'll put a plus here, and I'll put a plus here, and I'll put another plus, but I'll put a blue plus here, so that. So what do I want to write? I want to say that cost of dashed edges, because this is what is going to give me the new cost, is greater than or equal to the cost of the original edges. Okay, this is very weirdly said, but right. So these are the new assignments that I'm doing. Right, that the new assignment's cost is more than the original assignment cost. Right? So, because this is a locally optimum solution. So let's think of it as minus greater than or equal to 0. Yeah, so this is the new cost, this is the old cost, and that's negative. That's positive. Which is why cost of dashed edges I'm putting a plus, because this is a plus coefficient here. So instead of this cost, I'm saying it's this cost plus this cost plus this cost. Right? Let's put all for all of them. Right? So I took care of this one. Let's take care of this. So this was going here. So this length is at most this length plus this length and plus this blue length. Yes? And what am I minusing here when I'm doing this? What is getting minused out? Right? This is getting minused out and this is getting minused out in this expression. Right? So we are saying that these plus edges and these minus edges is greater than or equal to 0. Right? I'm just, instead of writing expressions, mathematical expressions, I'm trying to give you a pictorial proof for this entire thing. What about these? Right? I'm subtracting these, but these are not, which edges should I add a plus to? Right? These ones. Yes? Because we are saying this cost minus this cost. So it's overall put together, right? So this is some very large expression where these terms will appear at pluses and these will appear at minuses. And now let me quickly go and take care of the rest. So this will be minus, this will be minus, this will be minus, and and what will be the pluses? Okay, this will be a plus, this will, no, not this will not plus, sorry. So these I'm taking off. Now this is getting mapped to here, so this will become a plus. This will get a plus, this will get a plus. And there will be, for each one of them, I'm going to get a plus here and another plus on this one. This plus I'm going to get another plus on this one, this plus on that. Right? This is what it will look like. Now, who can tell me that if I write these inequalities, so I'm writing these inequalities for k pairs. How I form these pairs? I said I will identify a suitable set of pairs, but right now, because I have the simplifying assumption, I can pair anyone with anyone. Right? And there are k in the optimum k in mind, so arbitrarily I pair, so I get k pairs. And I write all of these inequalities for these pairs. Right? So let's ask ourselves, what will be the net effect? How many pluses and how many minuses are going to be? Okay. Khichdi lag raha hai, right? It looks complex. But let's think of it from, okay. Let's think of it from a one edges perspective, right? This blue edges perspective. Will it ever get a minus? It is getting a minus. Will it always get a minus? Will it always get a minus? Why?
It has to be assigned to some other.
Because this one of this facility will, whatever is this facility. So when I'm writing these k pairs, every facility in my solution is getting closed in one of the pairs. And every facility in the optimum solution is getting opened in one of the pairs. Okay? So this will always get a minus. Every blue edge will always get a minus. When will it get a plus? When will a blue edge get a plus? Yeah? Put it in words.
It is the mate of the.
When it is a mate for someone, right? And everyone is a mate for someone, right? Because of that simplifying assumption, and we said everyone. So every blue edge will also get a plus. Yeah?
What happens to the, like when we close facility I,
Yeah.
that it becomes a client, right? Now,
It becomes a client.
like when I is closed as a facility.
Oh, the client corresponding to I is also, you worried about that?
How do we take care of?
Like, see, so maybe the locations are duplicated here, right? So there is another one here, and we are just thinking of it in that term.
Okay.
Right? If that confuses you, think of the facility locations and the client set at this juncture. Okay. 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 Is that right? So I'll need a little bit of.
You're summing all pairs of IG. Like what is this?
Okay, so I'm picking some k pairs. Let's say I pick I1 J1, I2 J2, I3 J3, IK JK. Right? I'll pair them up arbitrarily. Okay, and I'm saying, okay, if this is the swap I'm doing, then what is the increase in cost going to be? And at every step, for every swap, the increase in cost has to be, the new cost has to be more than the original cost. Because if it were less, then this is not a locally optimal solution, right? Remember we said we are working with a locally optimal solution, and for any possible swap, the cost is only going to increase, the new cost is only going to be larger than the proposed. And that's what I'm thinking of, right? So, okay, so to recap a bit, so I'm saying I want to shut this, and here we said, I'm looking at this swap, maybe this is I4 and this is J4. Okay, so I'm saying I'm shutting this, I'm opening this, and this is how I'm going to reassign my clients, right? How am I going to reassign my clients? I'm saying, okay, all of the clients which are getting served here, I need to take care of them, right? I need to take care of them, and the way I'm going to take care of them is that I am going to, the clients which are getting served by J4 in the optimum solution, I'm going to send them directly there. But for all other clients, I'm going to send them to their mates, right? Or by sending them to their mates, I'm saying to the whichever facility is serving their mates in that mapping, right? So I created this mapping by looking at the balls corresponding to the facilities in the optimum solution, or the clients served by the optimum solution. I created a mapping between them, and I said each client is going to be served by whoever is, or is going to go together with its mate. That's the right characteristic of it. Right? Wherever the mate is going, this client is also going to go. Okay? And for a minute, forget about, so these two clients are in some sense special. Right? Why? Because they are going to the facility that got opened. Each of the other clients is actually going to one of the blue facilities only. Yes? And for those, we have argued that I will, so this is the distance that is in the new solution, this is the distance in the old solution. I put a minus here, and I put a plus not on this edge but on this path corresponding to it. And now with this I said, so for a minute we are going to forget about this. So we said every edge is going to see a minus and it's going to see a plus, each one of the blue edges. What can you say about the red edges? Are the red edges seeing any minus? No, they are seeing a plus. How many pluses will a red edge see?
Number of mates and number of uncovered after deleting this.
Sorry, come again?
After deleting I1,
After deleting, this is I4, but okay, it's I, yeah.
the vertex, the red edges adjacent to that vertex, those vertices.
Right.
And their mates.
Right. So we put pluses on all of these, right? Now let's say that, let's call this I3, right? And maybe this was J3. And when I shut I3 down and opened J3, then I3 was serving, in this example it was, let's say, serving only this one. Yes? Where will this client, who will take care of this client now? It will go to wherever its mate is. This is the mate. This is the mate. So this client will go to this mate. So which edges will get a plus and which will get a minus? This edge will get a plus. And which other edges will get a plus? These edges will get a plus. And this edge will get a minus. Yeah? So what we said, all the blue edges are going to get a plus and a minus. And all the red edges are actually going to get two pluses, exactly two pluses. And you can see why, right? Because, this is, when this client goes to its mate, we are going to put a plus on this client's edge as well as mate's edge. And when that mate goes to this client, we are going to put another plus on this edge and its mate's edge. So every edge is going to get two pluses. Yeah.
If we close I4, so why are we using the map type?
Right. Her question is, did we close by 4 and open J4, right? So, did we do that? Did we close I4 and open J4?
That's why we map to I3,
Yeah. No, again, as I said, this is all a mind game. We did not actually close this. We said, this is the locally optimal solution. This is the final solution. Once we have reached here, we are not closing anything. We said, if I had closed I4 and opened J4, then this is the inequality I would get. I have actually not done it because, if this was giving me an improvement, this would not have been the locally optimal solution at all. So it's not as if I'm doing these changes on this solution. This is only analysis at this point. I'm just writing the inequalities. I'm saying if we had shut this and opened that, then this is the inequality I would have got. If I'm shutting this and opening that, then this is an inequality I would get where I would have a plus minus here and so on. Yeah, you understand what I'm saying? Yeah.
That mapping is conditional on a particular J, right?
The mapping is defined for each J. Yeah. So the mapping is defined. So you take for each of these J's, you are looking at the client that J is serving, and you are setting up a mapping between those clients. And then for a different J, you have the set of clients it is serving, and there is a mapping. So there is one mapping over everyone, right? But it's defined per J.
For each client, there are like K mappings?
No. There is a single mapping. There is one single, that's what I'm saying. So you take, so this was a particular client J, as well as a particular facility J. You looked at all the clients in here and you defined a mapping over them, right? Now there would be a different facility, this is J1, there will be a different facility J2, this will be the ball corresponding to J2, and you will define a mapping over them. And this client, set of clients and this set of clients are disjoint. Right? So there is one mapping which is common to all of those. Okay. Now let's look at, so I separated these two things out, right? So there were these clients which were served by me and which were getting then assigned to blue clients, to the bottom, to my solution. But then there were clients which were served by me which were getting assigned to the red clients, right? Okay, so when I'm going to close this and I'm going to open this, I'm going to make a small change. I'm also going to say that if this was serving other clients, okay, maybe in the optimum solution there was another client here which was getting, not in my, okay, so this is this and this is, maybe it was served here. So this client that I opened, this facility that I opened was actually serving one other client, right, was serving some other clients also. So when I open this, I'll not just serve the clients that were getting served by here, by this one, but all these other ones also, right? Why? Because it does make sense, whatever opt is doing for me to be repeating that. So I'm going to also include these. And uska consequence kya hoga? Ki now what we will see is that for every client, so let me write down the statement. For every client J, the red edge gets a plus and the blue edge gets a minus. Right? So what are we saying here? So this is a bit, maybe for those of you who are seeing this, I guess all of you seeing it for the first time. So when I open a facility, so there are two things at play here. One is, of course, all of this reassignment, right? And all of this reassignment is going to create two pluses on every red edge. and 1 plus and 1 minus on every blue edge. This reassignment game that we have. And that means that when I sum up all of these inequalities, what do I get? So when I sum up all of these inequalities, what am I getting? If there are 2 red edges on every, 2 pluses on every red edge, so that means 2 times the cost of the optimum solution. And there's a plus and a minus on every blue edge, right? So which means 0. So this part is going to sum up to just this much for all of these reassignments that we are doing. But there's more happening, and the more happening is the part that I sort of ignored till now. And that part is, suppose this is J4 and this is I4. So what happened, right? When I opened J4 and I closed I4, I said I will put a minus here, and I will put, of course, there are more minuses, but I'm just now focusing on this part here, and I'll put a plus on all of these, and I'll also put a minus on all of these, right? What is this? This is not the reassignment part. So there are 2 parts that are happening, right? So one is when I close this, some clients need to be reassigned to other blue clients. But there is also the fact that I'm opening one new facility, and it is going to be serving some clients, and they are going to come to here no matter which facility they were getting served by in my solution, right? So this is going to happen for every client, right? So every client is going to see the red edge at a plus, because at some point or the other, the facility that this client was getting served by in the optimum solution is going to be open, right? So every client is going to see a plus here, and every client is going to see another minus here. So that's the second part. So this is going to contribute for us cost of O because of the pluses minus the cost of S because of the minuses. And so these 2 things are happening simultaneously. Okay, I messed this part up, but what are the 2 things that are happening simultaneously? So I'm shutting one facility of my solution, and then my responsibility is that all the clients it is serving go somewhere, right? And for that I had to do all this dashed lines, and I had to do all of this, and this game had to be played. But the simpler thing is that when I'm opening a new facility, right, all the clients that the new facility is serving in the optimum solution can all go there, right? As I said, I choose the reassignment. I decide who goes where, and the best is only better than what I do, right? So I say that you all go there. Clearly, that will mean that you will my cost will increase by this, but it will also decrease by this amount, right? So I'll get this additional term. So you put both of these terms together, and that's what you get. This is the outcome of the set of inequalities that I added up. And as you can see, this is now just saying that cost of S is less than or equal to 3 times cost of O, which means the cost of my solution is less than 3 times the optimum solution. Okay? I said 5, so why did I prove 3? Simplifying assumption, right? So if I did not have that simplifying assumption, then I have to do a little bit more work, and it requires another half an hour of a class or maybe longer. So, but you can read that up in the paper. So with if you don't make that simplifying assumption, which means you consider it full glory, then you get a 5 approximation. Okay. It might seem a bit tedious, but the message that we need to take is that in many of these local, I've done a lot of local search algorithms, and in almost all of them, the game is always the same, right? You look at a locally optimal solution, and then you say, because I could not make these moves. Remember, because the algorithm is done and cooked, right? There's nothing you are doing anymore. Because I could not make these moves, I can write an inequality. And now, if you can cleverly put together the right set of inequalities, you can then argue that the cost of your solution is bounded by some constant times the optimum solution. Okay?
Sorry, it's just a general question. Examples where the natural local search algorithm is provably bad.
There are plenty of problems for where that happens, right? So local search as a technique has been used, for many years, for many decades, for that matter. For instance, for TSP, you had a Lynn-Kernighan heuristic, which if you read up about local search, this is one of the first things that would come up. And the Kernighan heuristic was very trivial. It was saying you have a TSP solution at any point, you will take two edges of the solution and you will reconnect them in this manner. This is also called the two exchange heuristic. And you'll see if this improves the cost of the solution. And if it does, you make a change. And you keep repeating this. Right? Again, a very simple heuristic which works well in practice in many settings. But there are very simple examples. I don't have one offhand, but there are simple examples to show that this might actually, the locally optimum solution here might be much worse than the best possible solution. Okay? So for this problem, I will show you also an example where this 5 that I am arguing is best possible. And the example is actually very simple. Okay, I could have kept that. So this is k minus 1. This is k minus 1 by 2. For now, I assume k is odd. So this is k plus 1 by 2. Zeros and 2's. Okay? This is the optimum solution. And this in blue is the locally optimum solution. And this is the set of clients that we have. So first let's just quickly check that we can see what the cost of the locally optimum solution and the optimum solution is. So the optimum solution has a cost of, right, so these are ones, so it will basically have, these are only k plus 1 by 2 clients, so the optimum solution has a cost of k plus 1 by 2. The locally optimum solution S has a cost of, it's 2 times k minus 1 by 2, right, for these clients, and then another k plus 1 by 2. Okay? So this is k minus 1, this is k plus 1 by 2. Yeah. No, I messed up somewhere. Times 2. Okay. So k minus 1 by 2, this should be 4 times that, right? So this is the number of facilities. So the number of clients is k minus 1. Each of them are served by a cost of 2. So it's 2 times k minus 1. And so you can see this is roughly k by 2 and 4 times k by 2, and this is k by 2, so there's a factor of 5 there. And why is this locally optimum? Okay, so what would you have done? You would have shut down one of these facilities and let's say decided to open this. Okay, Okay, and assume that the distance between this and this is very far, or distance between each one of these is very far. Right, so the distance between these set of points and this set of points and this set of points is infinite, right? Very large distances. So if I were to open this and I were to close this, then this is already getting there. This going there would incur a cost of 2 plus 2 plus 0, right? So assume that this distance is given by the metric distances from this graph. So this is 4 and this is also 4. Okay? So if I were to open this and I were to shut this, then this is 4 and it doesn't give me any improvement, right? Because this is also 4. Right? If I were to open this, then both of these clients will have to go there because they cannot go anywhere else. So these are infinitely apart. And this would incur a cost of 4 and I'm already paying 4, so no improvement. If I were to shut one of these and open that, the same kind of a thing we could argue. If I were to shut this and open that, each one of these clients will go there, so that's 1. This will also go there, so that's 1. So that's k. I'm also serving them at cost k, so there's no improvement to be made. Right? So this is a locally optimal solution they have for this simple instance, and that's 5 times the optimal solution. Good, so I'm almost out of time. So yeah, this will seem a bit intimidating, but as I said, local search algorithms, very simple to specify, very simple to implement as well, but the analysis gets to be, trickier, and sometimes tedious, right? But once you have the right toolbox, it's not too difficult to do it. Right?
So instead of removing one item and adding one item, if I allow to remove constant number of items to be removed, and has it been studied?
Yeah. Oh, everything you think of has been studied, unfortunately. You guys are coming very late in the game. So, so that's called the P exchange, or P swap we call it. So what he's saying is, instead of replacing 1 with 1, suppose I decide to replace P with P, right? So that then gives a 3 plus 2 by P approximation. Right? So if you do P is 2, then it becomes a 4 approximation. So it goes from 5 to 3 in this continuous manner.
If the distances do not obey triangle inequality, then no local search.
Then the problem, I think, you cannot get better than a log n approximation for this problem. So it is, it's as hard as set cover is. Right? Because then you can embed a set cover instance into this, and there again the problem is you want to pick k sets to cover all the elements, right? So it's something like that, and so finding the minimum number of sets, you can model it in that manner, and you can get a log n hardness. More questions? Yeah.
Yeah. So the so regardless of how we choose the vertices j and I and j, whether it's greedily or randomly, the analysis holds. So the version of local search where we choose randomly or greedily will still give you that path approximation of 3.
Yes. Right, because we are saying that this is arbitrary, right? So for every, here you're saying that, remember, how's this analysis going? It's saying that this is a locally optimum solution. And when I say it's a locally optimum solution, I mean no swap could have helped me, right? So now whether you're choosing things randomly or something, till you are getting a locally optimum solution. How you get to that locally optimum solution is your business, right? But till you get to a locally optimum solution, this analysis would apply. And so you would, this performance guarantee would apply to any locally optimum solution.
So where are you using the fact that cost here is a sum? If I find some other cost function, weighted sum, or where are we using that cost exactly?
This triangles inequality. See, remember I replaced this dash by said this plus this plus this. So here I'm critically using the fact that it satisfies triangle inequality.
Not on the triangle inequality. I'm just saying the cost of a set S
Yeah.
is sum of the distances covered. Instead of if I say, like if I define some other function saying that is what I want to minimize,
Yeah.
not the sum exactly.
Right.
So where are we using?
Yeah, so everywhere we are in some sense using sum, right? The entire analysis we are, looking at where is this client going, and then we are summing up all of these costs, right? So, but what you are saying, so I also mentioned at the start of the class that about the k-means problem, right? And in k-means you are looking at squares, sum of squares of distances. Now, this entire analysis also applies there with some small modifications. So you can use this analysis. So instead of here, I was replacing this with this plus this plus this. Now I'll have to replace it with, so there is where the difference will happen because it's sum of squares of distances. So we'll be looking at the square of this distance and we'll have to bound it by the sum of squares of this, right? So that's a place where small changes will have to be done. And then, but broadly this analysis gives rise to a 9 approximation for the k-means problem. The same algorithm, right?
Also minimize the max.
Sorry?
Also minimize the maximum distance.
Okay, minimizing maximum distance, as I mentioned at the start, is the k-center problem. So here, find k points such that max distance of any point in V to max of nearest distance to this set is minimum. Okay, formally I could write it as you're finding minimum over all choices of S, max over all j belonging to V, distance of j to S. Right? So you want to find a set of, size of S is k. You want to find the best set S such that the distance of j to S, the max over all j. Right? So this is called the k-center problem. And the best is a 2 approximation. It doesn't use local search. And this is also the best possible, right? You cannot get a 2 minus epsilon approximation.
If this local search algorithm still makes sense for this.
Does the local search algorithm make sense for k-center?
K-center might be equivalent to maximizing the product of non-zero distances, like I'm trying to balance.
No, k-center is not trying, k-center is like an L infinity matrix, right? You can think of this as an L infinity metric, right? Because you're looking at max, while k median is, instead of max, you have sum, right? So it's the L1 metric and k means is the L2 metric. So you could talk of any P metric. Will k-center, I'm not sure, right? So maybe this local search would also work for k-center, but I'm not certain.
I was just making sure the algorithm is well defined, but
Yeah.
the analysis.
See, local search algorithm, one can always define a local search algorithm, right? What matters is are your local steps powerful enough to give you a good guarantee on the quality of the solution that you get at the end, right? And in subsequent results on using local search for facility location, there have been actually this is very simple, right? You're just taking I and j and you're saying isko swap karke whether it improves cost or not. There you have to do more clever local search operations, right? To be able to get a good analysis, right? To be able to get a good solution.
So I have a question actually.
Yeah.
So he was talking about randomness. Maybe we can avoid this example with inequality if we have random points at the start. So maybe we don't end up there mostly.
If you have an initial random seed or a starting set, could you have avoided this? See, the current set of techniques we have do not benefit from the choice of a seat, right, or a starting point. Because what we are saying, and you've seen this in analysis, right, you look at just what the final solution you have, and how you got to that solution, you're sort of you're not able to factor it anywhere. So I'm not aware of any work where the initial choice of how you pick the points gets reflected in the analysis, right? So that would be open thing to try. ठीक है? चलो good. Oh, you have a question.
What about approximating in both fronts, like setting up some more facilities and minimizing resources?
Yeah. Okay. So that those tend to be easier problems when, say, if you're the constraint that you have to open K facilities, if you're willing to relax that, if you're allowing, let's say, K plus log n facilities or 2K facilities, then it becomes an easier problem to solve. And I think there might even be like the 1 plus epsilon approximations available. Right? I'm not certain, but it becomes much easier to solve. So this keeping the number of facilities at K is a hard constraint, and when you have these hard constraints, somehow local search becomes a good vehicle to try and solve those problems. But yeah, so when you relax that constraint, you make it softer, then it becomes easier. Right?
The solution set of the max problem, like minimizing the max, and the solution set of the sum problem, like are they like in any way close, like cost will not be?
Or you're thinking whether I could find a S which sort of does both the things, is it?
Yeah.
Both max and sum.
Yeah.
Like you said, the numbers have large variances.
Sorry?
If the numbers involved here have large variances, not because.
Set up some control techniques.
Yeah, I'm wondering whether some example can be set up. See,
How bad could a solution for the max problem be in terms of the sum? I mean, it could be like.
yeah, because okay. So one thing that has also been looked at, actually, no, that's a open problem in this setting, is K median with outliers, right? So quite often you have this set of points, but you don't care for serving everyone, right? Because maybe some are really outliers, and so you want maybe 5% of the points to be thrown away. So that is something like marrying K center with because if you were to think of their distance from these set of points would be very, very large. So the K center value would be very bad for those points, right? And but for this problem, for K median, that has been open for a very long time to do K median with outliers. So that is an open problem. There are other versions of facility location which have been done with outliers, but not K median. Okay, good. Nice talking to you guys. Thank you.
morning everyone. This is our last speaker session for the summer school. So yeah, Professor Akash Kumar is going to be speaking on hardness of approximation. I would just like to make two announcements. The first one is that we'll be sending you the Google form for the feedback and the reimbursement after the summer school ends. You can expect it maybe today or tomorrow. And certificates will be given in the last session, which we call discussion, but we're not going to be discussing a lot. So yeah. We can discuss, but we'll give you the certificates first. That's it. Okay, let's welcome Professor Akash.
Thank you. So, today I would like to tell you about hardness of approximation. It's a beautiful area. But in my opinion, two of the best people who could have done this job way better than me. None of them are in the room. One is Professor Anand Lewis, who is a faculty member at IISc. The other one was, in fact, Professor Naveen Garg himself. Yeah, Naveen can do everything better than anybody else. So yeah, that's not saying much. All right. So I want to tell you about hardness approximation, and let me begin with an advertisement. Okay, so it's an advertisement for this area. There is I really have no business evangelizing hardness because people have evangelized the hell out of it. But the idea is that this area is still cool. So let's think about what kind of theorems this area allows you to prove. Okay, so here is an advertisement. So here is a problem. So the class NP contains languages, right? 3SAT is a language, Max Click is a language. All these problems are languages, all right? So I'm going to consider a language. This language is called math. Okay, it's the collection of all those theorems. So T is a theorem. Actually, I should say it's a theorem statement. Might not be true. It could be a false statement. Okay. So, for example, it could very well say this language math can contain statements of the following form. That in any right angled triangle ABC, a square plus b square equals c square. And it might contain the statement that in any right triangle ABC, a square plus b square is not equal to c square. One of those theorems is true, the other one is false. Right. So it's a language, right? And just like in any language, you have some instances that belong to 3SAT, some instances that are not satisfiable, right? All of that. So similarly, some things that are valid theorems, some things that are invalid theorems. They're just mathematical statements. So T is a statement of a theorem which admits a proof which is, let's say, less than some n pages long. Think of n as being some generously large number. And if you really want to obsess about those details, you can say font 11 and spacing normal, all of those things, right? Yeah. Okay. So what do we know? Yes.
So this basically it means a poly-size certificate.
That's correct. Yes. Poly-size certificate, poly-size proof. So if you want to be more pedantic, you can say something more. That a poly-size proof exists in which system? Okay. If you are being that pedantic, you really should not. There is no reason to be that pedantic, but sure, let's entertain that thought. So I'm talking about proofs in an axiomatic system, which is rich enough to so for example ZFC, right, which generates, which has sufficient ability to contain interesting proofs, and those proofs better be verifiable in time polynomial in the length of the proof on a standard deterministic Turing machine. Okay, so if you did not get all of that, don't worry. This is the language I care about. That I'm looking at a bunch of statements, possibly true, possibly false. That's what I would like to think about. I would like to think about membership in the class math, okay, of a certain instance. Now the question is that, what PCB theorem states is something fantastic. So let's think about checking a proof, right? You have possibly read several proofs you saw already in this summer school, all right? Okay, so for example, yesterday you saw a proof of 3-factor approximability of the multi-cut problem in Professor Naveen Garg's class, right? So how do you verify a proof? That's what we would like to think about. And it seems that the task of verification is a very laborious task. You read one line, you read the next line, you read the next line, on and on you go. It's a sequential task, okay? And if your proof, God forbid, has a mistake, so maybe you read my proofs and I'm a malicious prover. I'm not a nice agent, I don't play nice. So I produce flawed proofs all the time, right? So now what will happen is that if in a particular location I adversarially switch a 1 with a 2 and you did not catch that, then I could prove that like, big O of 2 power n like is in fact polynomial, right? So yeah, I could prove like all kinds of nice theorems that I would love. You wouldn't, but the idea is that like, a malicious prover could mess with you if you're not careful in verifying the proof. You have to really verify the proof line by line. At least that's what we have been trained to think. Okay. So the punchline of PCB theorem is that the rabbit hole goes way deeper. Okay. So turns out that there is a way to rewrite your mathematical proofs. So given any mathematical proof, what I can do is that I can rewrite that proof in a fantastic way. It will produce a blown up proof. Okay. This proof would be gigabytes and gigabytes long. Okay. But how do you check this proof? Just flip open a random page, check a random line. It doesn't get cooler than that. Okay. Flip open a random proof, check a random line, and I'm not bullshitting you. Okay. So this is what PCB theorem actually asserts. So the idea is that PCB theorem asserts qualitatively that the notion of proofs that you knew can be robustified. That is, valid proofs will remain valid proofs, but if I give you an invalid proof, even if it is the tiniest mistake, perhaps an honest to goodness mistake, perhaps it was an honest typo on part of some student, but what will happen is that the echoes of that mistake will show up everywhere. Okay? How do we prove anything like that? Question 1. Question 2. Looks like that this would be something that Kurt Gödel and other logicians will be very happy with. But what has this thing got to do with computer science? Okay. So here is where I get to flash advertisement number 2. It has got very deep connections with approximation algorithms. Okay. This should again be a shocker, but maybe not such a big shocker if I tell you that think that the problem 3-SAT, I'm going to make an assertion about it. 3-SAT cannot be solved in polynomial time. This statement, 3-SAT cannot be solved in polynomial time, it's a member of the class math. It's a statement. It's a mathematical statement, a well-formed mathematical statement. It belongs to the class math. But I know that proofs of math can be robustified, that any language, the proof of any theorem in the class math can be robustified. That's the content of this mysterious PCB theorem that I have not yet flashed. Okay? But once you understand the proof of PCB theorem, the consequences are far-reaching. They just send your head spinning. So what will happen is that you would realize that if you look at a 3-SAT instance, what I can do is that maybe this 3-SAT instance was almost satisfiable. You tried an assignment and you were like that, oh, I did pretty well with that assignment. Let me try a new one, a tiny variation of this, and maybe this time I would be actually able to satisfy this 3-SAT instance. You keep trying, but maybe there is a situation in which there is just one annoying clause, right, which is always false. So you try some assignment, clause number 10 is broken, you try a variation of this, exactly clause number 20 is broken. So the broken clause keeps moving from here to some other location, and you're never able to find a satisfying assignment. What PCB theorem tells you, if you apply it to this statement that 3-SAT cannot be solved in poly time, if you apply it to that statement, what you would get is that I can produce a new 3-SAT instance. So I look at my old 3-SAT instance, I can produce a new 3-SAT instance for you, where whenever it's falsifiable, it's not falsifiable merely, it's falsifiable blatantly. All assignments will falsify at least 1% of the clauses, not just one clause. All assignments will falsify at least 1% of the clauses. Right, so this is again far-reaching. That how would I test how good an assignment is doing? I would just check a random clause. I check 100 of them at random, and since 1% of the clauses are broken, if I checked 100 random clauses, if I inspected 100 random clauses, I would find a broken clause with good probability. So this is what I mean when I say flip up in a random page, check a random line. So that's PCB theorem. Okay. So the stage is set. The intrigue is set, but what remains to be done, is a bunch of setup, which might be a bit annoying. So you have to bear with me. If you want to see the surprise, I don't think I'll be able to communicate all the surprise in full glory. But what I can do is that I can like set up the stage and tell you about some cool things. So let's do that. So to begin with, I would like to define an approximation algorithm.
Sorry, a small clarification about math. Is this like math sub n or like what?
This is math sub n. Good point. Very good point. So this class math should be really written as to indicate that the length of the input is n. That the proof is supposed to be polynomial in some parameter. What is that parameter? That n. Good. So now let's make a definition. Approximation algorithms. So I'll be defining things that you kind of instinctively know, but it's important to write those definitions once and for all so that we actually know what we are staring at. Okay. So I'm going to define approximation algorithms only for NP-hard problems. An approximation algorithm for an NP-hard problem, capital P, is a polytime procedure, polytime algorithm I would say, which on any instance I, so you take some instance of this problem, take some instance of a problem, think vertex cover maybe, so you take a graph, right? What it does is that this algorithm outputs a solution with value AI such that what you have is that this value for maximization problems at least gets an alpha fraction of the optimum value. So for example, for max cut, you get maybe 0.878 of the optimum value. Right? This is for maximization problems. For minimization problems, you would say that A of I should be at most alpha times opti. And of course here I'm allowing alpha to depend on the instance size. So you should think of alpha as being potentially a function of n. It could be a constant but does not have to be. Okay? So that's what I mean when I say approximation algorithms. Okay? Now I would like to define hardness approximation.
So these problems are optimization as opposed to decision?
For now, think that. But like you know, the decision versions are also fairly easy to state. For now, let's stick with this. So again, I should like repeat that what I erased. You don't have to take notes unless you really want to, okay? Because all the notes are available. So now I want to define hardness of approximation. This would allow me to introduce a notation that I will use in the rest of our discussion. So like the idea is that like what you say is that under suitable complexity assumptions, what I would like to say is that there is no approximation algorithm which achieves a beta factor approximation. Okay, so that's a pretty informal definition, but this will allow me to introduce a notation I've been like teasing a little. So the way I would like to do this, the way I'd like to introduce my notation is by giving you a bunch of examples. So let's see what kind of example problems you could think about. So here are some example problems. Then I would have the approx ratio. And then finally I have the hardness factor. So you know, the way I'm going to state this is that as I go down my list, the approximation factors will grow worse and worse. Okay. So to start with, I will start off with some easy problems. So for example, you have the bin packing problem. Does anybody remember what's the best approximation we know how to get? Okay. You can get p-task for bin packing. Okay. You can get arbitrarily good approximations. So 1.1, 1.0 and 1.000001, whatever you want, you can get that. Okay. So there is a p-task. Since I have a p-task, I don't care about the Hardness factor. It's like pretty much exactly solvable for all I care. I'm using the language loosely, but yeah. For 3-SAT, line gets interesting. So you should really think of this as maximization version of 3-SAT. The question that is being asked is that I have a 3-SAT instance. What is the largest fraction of constraints that a assignment can satisfy? Okay, that's the question we are asking. So turns out, does like maybe some of you know the answer. Would you like to shout it out? 7 over 8. 7 over 8 is doable. A tiny bit better is not doable. Yeah, that's the kind of conclusions you get to draw once you have a good mastery over this PCB toolkit. Vertex cover. Factor 2 is possible. Any better than 2 is not possible, assuming unique games. The complexity assumption is something called the unique games conjecture. It's still unproven, like a conjecture with deep implications, but we can't get into it today. So next one, we have set cover. Best approximation possible? Log n. And you know what's the best hardness we can do? You can't beat log n even by a tiny amount. Okay. Approximation factors are getting worse. Slowly we are encountering problems which we cannot approximate to within a factor of something that grows within. Right? So approximation factors are worse. Finally, I have the clique problem over here, the max clique problem. So max clique problem, what does that ask? It asks you the following, that I have a graph. What's the biggest size clique that you can find hiding inside this graph? Okay? And the results are pretty drastic. So what the result tells you is that, you know, the best approximation algorithm that we know is in fact factor n, right? So graph contains a gigantically large clique, and the best our polynomial algorithms know how to do is to output a single vertex. Okay? So that's pretty embarrassing, but yeah. And what's the lower bound that we know? All right, so the lower bound that we know, so like you know, n to the 1 minus epsilon, so like that's a pretty gigantic gap. So this is the state of the affairs that I summarized for like you know a handful of problems. These are just representative problems. The PCB theorem, it has been used to prove hardness for a bunch of more problems, like several problems. Okay. So that's the first thing that I wanted to get out of the way. Yes.
Can you also mention what complexity results are you using?
So wherever I have not written anything, it's just P versus NP. P not equal to NP. Yeah, I mean there is like just so many boring definitions that I have to give that it's perhaps best to set it up by like you know doing the advertisements first. Okay, so with that out of the way, let me tell you what is our plan for today. That was not the plan. Okay, so the plan is to tell you what happened before the PCB theorem was established, okay, and tell you a little bit about what happened after PCB theorem was established. These things, while I'm interested in doing those, the main event for today, the main takeaway, is to really go back to our advertisement discussion. So the main goal is to really understand that advertisement. Okay, so there are two different views of the PCB theorem. One is the proof view, where we try to robustify proofs. Okay. The other one is what is the connection of these robustifying proofs with approximation algorithms, or inapproximability as it is called. That I cannot get approximation algorithms which can provide an approximation better than a certain factor. So I'm telling you something pretty mysterious. It will not be that mysterious once the dust settles, But what is supposed to be mysterious right now is that there is supposed to be a connection apparently between this proof view that you can robustify proofs and this approximability view. By the way, I don't know how many of you are aware that so I don't know much about this stuff, this blockchain thing, but turns out that all of this blockchain technology is a heavy user of the PCB machinery. If PCB machinery or the technology to robustify proofs did not exist, blockchains would not exist. So the story is something like this, that you claim that you have some bitcoins, you did not steal it from somewhere. Like I don't have bitcoins, I don't know why people care about bitcoins, but okay. So you have some bitcoins and you want to claim ownership of those bitcoins. So how do you provide a certificate that it is actually you who owns these bitcoins? So you print out a PCB proof, a blockchain, and what a verifier or like somebody who wants to do some transaction with you using those bitcoins, what they can do is that they can verify by locally checking this gigantic gigabytes after gigabytes sized proof that here is a small certificate, some tiny little snippet in this gigantic proof that kind of authenticates that this guy is in fact the legitimate owner of those bitcoins. Okay, so yeah, I mean this technology is actually relevant. So yeah, the main takeaway for today's lecture is the equivalence of the proof robustification view and the inapproximability view of the PCB theorem. We have a long journey ahead of us because what I want to first tell you about is what we knew before the PCB era. We did not know much. So for example, the only two examples that come to my mind is inapproximability result for the traveling salesman problem and the inapproximability result for the edge disjoint path problem. Also called EDP. Post PCB, we know a whole bunch. A lot of things were collected over there. One of the examples that I really like is the so-called linear equations in 3 variables over F2, but I don't think I will get to it. Okay, so let's get started with TSP. By the way, can everyone see that picture over there? I draw that picture beforehand. Made that picture beforehand because, yeah, drawing it takes too long for me. First, let's think about TSP. So the claim is that you cannot approximate TSP to within any factor that you like. Okay. So my graph has edge weights, it's a complete graph. That's what a TSP problem is. The graph is always a complete graph. But the edge weights do not satisfy triangle inequality. I'm making no such assumptions. Okay. If the edge weights satisfy triangle inequality, you know how to get a 3/2 approximation. Right? So edge weights do not satisfy triangle inequality. Let's see what you can do. So the reduction, so I'm going to claim that you cannot get factor 1000 approximation. This 1000 you can easily make 1 million or even n. Right? So does not really matter. So there is no approximation algorithm for TSP with factor 1000. So here is my reduction from Hamiltonian cycle. So Hamiltonian cycle is a problem that asks you that I give you this graph, can you find a Hamiltonian cycle inside it? The input for Hamiltonian cycle does not have to be complete enough. Okay? So it's just some graph. So the graph that I'm going to take is the following picture. Actually, let me try it slightly differently. So that's the graph you are given. Here is the graph my reduction machinery will compute. So this is your original graph. All edge widths are 1. So I retain all these black edges. Alright. All these black edges, they have weight 1. But I insert some red edges to make it a complete graph. Yeah. All these red edges, I'm going to put their weight as something. What should I choose as their weight? Yeah, very high, but what?
Either sum of everything or 1000 and
1000 N. All of them have weight 1000 N. So now let's think about what happens. If this guy had an Hamiltonian cycle, over here would emerge a TSP tool with cost N. If this guy does not have an Hamiltonian cycle, any TSP tool will have cost at least 1000 N. Right? Game over. So this is what reduction proofs kind of look like when you want to conclude hardness or approximation results. It's a reduction, it's a classic reduction. But somehow you have to produce a gap. And that looks kind of unwieldy. Because you have the following classic picture. Here is the space of all three set instances. You have the yes instances over there, the no instances over there. If you want to establish a hardness of approximation, you want to somehow push these yes or no corners apart, these poles apart. Right? So that's what you have to do. So yes corner, yes elements of the target problem live over there, no elements live over there, and there is some gap here. The entire challenge is how do I get a gap? Okay? So we will think about this slowly, but let's take another example, the edge disjoint paths problem. So let's first introduce what the setup of that problem is. So this is a more interesting example. So I heard Subhash Kot once claim that the only two examples that he knows which are interesting to him, so TSP is not very interesting for him, but the only other interesting example of hardness approximation that he knows of is the edge disjoint paths problem. All other examples, I mean the pre-PCP era. At pre-PCP era, this was the only other example that he thinks has a bit of non-triviality going on. So let's introduce what the edge disjoint paths problem is. So the EDP problem. You are given a graph which is directed, and what you are trying to do is you are trying to understand that given a collection of sourcing pairs S1T1 all the way up to SMTM, right? You want to understand, you want to ask that what is the maximum number of SITI pairs that you can connect when I force you to use paths which are edge disjoint. That's the question. You want to essentially look at this picture. You have S1, S2, maybe SM, and then T1, T2, TM. You want to essentially route SIs to TIs. Right? And you want to keep these parts disjoint. That's the challenge.
Flow decomposition में paths edge disjoint.
Yeah. I mean, so that's the kind of algorithmic thinking that you would use. But this constraint of you being forced to use edge disjoint paths is going to cause a lot of nightmares. So here is the theorem that I would like to state. So the theorem is that you fix any sufficiently small positive epsilon, right? Then it is NP hard to approximate EDP within a factor of roughly square root number of edges. Square root number of edges is e to the 1/2 minus epsilon. So we already know how to get a square root E approximation. Right? So a bunch of pairs are routable, right? But the best that an algorithm can get is opt over square root E. Okay? And like we know that you can't do even a tiny bit better than that. So that's the result that I'd like to prove. And the way this proof works, the way this argument goes is by relying on the NP hardness of what is called a 2EDP problem. So, let me recall or define, maybe not recall, the 2EDP problem. So what 2EDP asks you is that again you are given a directed graph. And you are given two sourcing pairs, right? X1, Y1, X2, Y2. The question is, can you route X1 to Y1 and X2 to Y2 while maintaining edge disjointness of these paths? Okay, that's the question. So the picture is kind of like this, that you have X1 over there, Y1 over there. Can you solve this routing problem? That's the challenge. Okay. What we know is that the 2EDP problem is in fact NP hard. So this is something that we are just going to use black box. And now once you are willing to use this in black box, what you can do is that you can finish up with the task that we are after. You can conclude the almost square root number of edges hardness for the EDP problem. Let's see how we'll do that. So over here we have a picture. Here I have listed for you the n sinks over there, the n terminals over there. And like I'm connecting them up in this way as it is suggested over here. The annoying thing that I do is that at every single intersection, I delete that intersection and what I put in over there instead is a copy of this EDP instance. The copy of this mysterious EDP instance, which you don't know whether it has as disjoint paths connecting X2 to Y1 and X2 to Y2 or whether it's no instance of 2EDP. So I put over there like a yes or a no instance of EDP, that's a subgraph that I'm calling G. And now the claim is the following, that like so maybe this is something that you can sense, that suppose that this graph G was in fact a yes instance of 2EDP. That is routing from X1 to Y1 and routing from X2 to Y2 via S disjoint paths is in fact possible within the graph induced by G. And what I am doing over here is that at every single intersection I do the same thing. At every single intersection I have a copy of that red graph G. So here I have a copy of red G, here I have a copy of red G, on and on and on. Okay, here I have a copy of red G everywhere. So the question for you is that suppose the graph G was a yes instance of 2EDP, what do you have over there? Is that a yes instance? What do you think? How will you prove it?
All of them are pairwise, like all pairs are pairwise, not
Good.
being intersected.
Yeah. You just follow your nose. So I mean like pretty much like you will connect S1 with T1 and like you will hop over, you will hop over. Yeah. So just do the straightforward thing. Yes instance is in fact being mapped to yes instances. On the other hand, so like maybe I should say that that if G was a yes instance of 2EDP, the reduction produces for you a graph H, which is in fact a yes instance of EDP, which means that opt of H is in fact n, because I could route all the n sourcing pairs. Okay. What you discover, and this is not something I'm going to like rigorously prove, I'm going to hand wave this part out. If G was a no instance, over here, opt of H would be exactly 1. Okay. And like the reason this would happen intuitively speaking is that if you could route Si to Ti and Sj to Tj, so here is Si being routed to Ti, here is Sj being routed to Tj, then what you can conclude is that there exist two edge disjoint paths inside the graph G. which we know do not exist, right? Because G I started out assuming was a no instance. Okay? So if I could in fact route Si to Ti and Sj to Tj, like, yeah, I mean I have to be careful in this part, right? I have to be careful in this part. So I have to avoid intersections. Somehow my instance of 2EDP better be a yes instance, but I know it's a no instance. So such a routing was not possible. Yes?
What is the diagram in between the structure?
So diagram in between here is a copy of the 2EDP instance. This instance is possibly a yes instance, which means that I have edge-destroyed paths available from x1 to y1 and x2 to y2, or it's a no instance, in which case no such path system is available. Okay? So you do not know, so it's a question mark. So the instance that's being planted over here is an instance of 2EDP, right? And you do not know whether it has edge-destroyed paths or whether it does not. In case it had two paths, you'd be able to route all sourcing pairs. Does that make sense?
Although it is clear, maybe you can show the planting by showing how there are n floating vertices, but only the terminals are connected to those grids, right? So
Yeah.
if you zoom into one of the plantings, maybe that.
Yeah, I mean, that would take me too far from what I plan to do. But yeah, I mean, unfortunately, I'm sorry, I cannot go into more details here. The entire idea is that, look, I mean, I could produce an instance for you pre-BCP era without using any heavy machinery, where there is a huge gap between opt-h in the yes case and opt-h in the no case. But the thing that you want to look at is how many edges are sitting inside h. So the number of edges sitting inside h, I have n squared sourcing pairs, n squared times the number of edges in G. Right? So the hardness factor is really square root of the number of edges in G, roughly speaking. Alright? So that's the pre-PCP era part that I wanted to talk about. I mean, if you want to look at it more carefully, you can look at the paper by Venkat Guruswamy. The argument is pretty short. It's a very short argument. But yeah, unfortunately, I don't have time to go in details of that argument, because I also want to tell you about the two equivalent views of the PCP theorem, which we can do now. So I'd like to tell you yes.
Can you repeat how we got root and edge?
Good. So opt-h in the yes case is n, opt-h in the no case is 1. Okay. But now let's think about the number of edges in h. How many edges are appearing inside of graph h? So there are n sourcing pairs, right? So the number of edges is n squared, right, times the number of edges in a copy of G. Because at every single intersection I have a copy of G hiding. Okay? So that becomes under the 2 plus epsilon if you do that more carefully. And that's why you get n to the 1/2 minus epsilon. Right? Number of edges in h to the power 1/2 minus epsilon. Again, if you really want to look at this argument in more detail, I'm forgetting the name of the paper. But just search Guruswamy, it's his 97 paper, and it has the word edge-disjoint paths in title. Okay, so now I can tell you about the two views of the PCP theorem. So let's begin with the first view. And so far I have been using the word PCP theorem over and over again. I have not yet expanded out what PCP stands for. Anybody volunteers to do the job? What does PCP stand for? Probabilistically checkable proofs. So here is the first way in which this statement of PCP theorem can be written. Then I will describe how to write it in another way. If you ask experts like Professor Prahlad Harsha at TIFR, so he is very fond of saying that these are not two sides of the same coin. This is the same side of that coin. So that's how he thinks about it. But yeah, I have definitely not reached his level of expertise. For me, these are still two separate sides. Yeah. So the theorem that I'd like to state. So before this theorem, maybe I should give an example. So I should give a definition. So I want to think about a problem that I'm calling gap 3-sat 1 alpha. So this refers to the following problem, that the yes instance of this decision problem refers to all 3-sat formula phi phi is a 3-sat formula in which every single constraint can be satisfied. Every single clause can be satisfied. So it's written value of phi being 1, right? And the no instance refers to the situation where you have a 3-sat formula whose value is less than alpha, which is less than 1. So I'm parameterizing the 3-sat problem with 2 new parameters. One parameter I'm just calling 1. You could also make this a different parameter alpha prime, but let's keep it 1. So in this instance, I promise you that the instance that was given to you satisfies every single assignment. The challenge is, can you find one? Okay. Or like overall the challenge is that the no instance, I'm cutting you some slack. In the no instance, what you know is that all satisfying assignments satisfy no more than alpha fraction of the clauses. Alright. So yeah, all satisfying assignments satisfy at most alpha fraction of the clauses, then they falsify at least 1 minus alpha fraction of the clauses. That's the promise that is being given to you. And now the challenge is, can you tell these two instances apart? Okay. So that's the gap 3-sat problem. And now with this definition out of the way, I can tell you the first view of TCP theorem. So this theorem asserts the following, that 3-sat, maybe I should say, there exists a constant alpha 0 less than 1 such that 3-sat reduces in polynomial time to gap 3-sat. Okay. So this is the hardness of approximation mu, that you cannot get good approximation algorithms. That's what this is essentially asserting. If you could get better than alpha 0 fraction approximation algorithms, it's an easy exercise to see that you could distinguish between the yes and the no instances. Okay. Right. So having a solver for having a very good approximation algorithm for gap 3-sat, for max 3-sat allows you to solve this decision problem. So that's view 1. Alright, so yeah, do I want to say anything else about it? No, I can just introduce view 2 now, I think. Even in order to introduce view 2, there is some more definitions I have to give. So that's life. So it turns out, how many of you know that the class NP could be thought of as a dialogue between two players called prover and verifier? Anybody heard of that? Okay, I mean, so class NP, like the proof verification view, how many of you have seen it? Like, I mean, please feel free to raise your hands because, okay, like seems like not many people are raising their hands, so I'll just like recall that like NP is the class of those decision problems membership for which can be verified efficiently. So you give me a proof, I can verify it, but if you ask me to come up with a proof, yeah, I mean, I'm having a hard time, right? So for example, you could give me a 3-sat instance and a satisfying assignment for that. I can verify that this assignment in fact satisfies the 3-sat instance, alright? Or I can also verify that this assignment is bogus. It does not satisfy the 3-sat instance. So in the rest of this lecture, I'm going to use the word proof, and whenever I say proof, I really mean a claimed proof. The claimed proof could be legitimate proof or a bogus proof. I will try my best to, like, disambiguate a situation that, like, proof could potentially refer to a bogus proof, but like that's what like will be the spirit of our discussion from now on. So in order to make sure that the proof that I'm talking about could be legitimate or could be bogus, you do not know, I would put proof in double quotes. Okay. So let's see what like this view is telling us. So this means that if my language L belongs to the class NP, then for every string x, if x belongs to my language, what you have is that there exists a proof pi such that if or an assignment pi, so string of x is a 3-sat instance, L is the 3-sat problem, pi is an assignment to the 3-sat formula. So if the verifier is given the 3-sat formula and the assignment pi, the verifier will accept. And for every x, if x is not in my language, no matter what assignment you try, I, the verifier, will reject. The classic thing, like nothing deep going on here. So the cartoon picture to keep in mind is that, like, here is your instance x, here is my proof pi, possibly a much larger size, still polynomial size. The verifier gets to look at both of these things. Verifier, I remind you, is a deterministic algorithm, and verifier can now output its decision. Yes, I accept, no, I reject. Okay. That's the classic view of the class NP in the prover verifier language. So it turns out that this prover verifier language is precisely the language that I will use to restate PCP theorem in a different way, to state the view 2 of the PCP theorem. But before I do that, there is a few more remarks that I want to make. Right, so yeah, and I think I can directly go and state the view directly. Yeah, so let me state the view first. Yeah, okay. So again, the setup is going to be the same. I will start with some language in NP, and then I will think what happens for various strings. Some strings belong to my language, other strings do not belong to my language, and this view is going to tell you about what happens with those strings. So the idea is that, like, take some language L in NP and take some string x. If x belongs to my language, then what I have is that there exists a proof pi such that, and now suddenly we are invoking probabilities. Now the verifier is randomized. Verifier can toss coins. The probability or the random strings of the verifier, that the verifier, when it looks at the string x and the claimed proof pi, right? So pi is a claimed proof, accepts is exactly 1. And if this string does not belong to my language, then no matter what proof you give me, no matter what fake proof you try to generate, the chance that verifier will reject or will accept, let's say, is at most 1/2. So you can't trick this verifier like really all that much. So the picture changes very slightly. You have, or maybe drastically depending on how you want to state this. So here is my proof pi of size poly n, and here is my verifier, which is now a randomized algorithm. So the remarks that I would like to make is that even though the verifier is a randomized algorithm, it does not make too many queries. The way this PCP view is written is that it should really be parameterized with 2 additional parameters. So the 2 additional parameters that I need to think about the PCP theorem are called R, the number of random coins, and Q, the number of queries. So you should really think that something like the following is happening. That you are the verifier, you have logarithmically many random coins, right? You toss these random coins, out comes some output, some arrangement of these log and random bits. Log and random bits can index into a proof of size poly n, right? So suppose I have 2 log and random bits, right? These 2 log and random bits can be used to index into a proof of size n square, right? So you toss these 2 log and random coins, or like however many random coins you have, 10 log and random coins, something. So these allow you to index into a certain proof. So for example, let's say I have like maybe, I don't know, 30 log and random coins, and so these can be, and I break these 30 log and random coins into chunks of 10 log and random coins each. I break into 3 chunks of 10 times log and random coins each, okay? So each chunk of size 10 log n can be used to index into a proof of size n power 10. And in this gigantic proof of size n power 10, I can read 3 locations, right? So those 3 locations refers to this quantity q. Okay, the number of queries I am making. So in order to like unpack this, I want to make a few more remarks. So the remarks I would like to make is that tau in fact refers to the random coins that the verifier is allowed to toss. The size of tau is in fact big O of log n. Q is the number of locations in the proof pi that verifier inspects. And like in fact we have to keep in mind that Q is big O of 1. Verifier is not allowed to inspect too many coins. So this is what I mean when I say that how to check a proof in this robustified framework. Flip up on a random page, check a random line. Toss or log and random coins, these tell you what place to look at, and check a random line. That's specified by this quantity q. Okay? So that's how like really, I mean this entire framework is to be viewed. I'm aware this framework is a bit bulky, but like it's not too bad. Right? I mean all things kind of seem to fit together. That I have log and random coins, I toss them, out comes a random page, I just query that random page. That's all which is happening over here. And like, you know, the other thing that maybe I should mention is that depending on the outcome of your coin tosses, depending on tau, what will happen is that the verifier is supposed to say that I accept this or I reject this. That's all a verifier is supposed to say. Right? So depending on the outcome of the random coins, the verifier inspects q locations. So those q locations, I will tell you what those are. So all of them are functions of tau. So verifier inspects locations I1 of tau, I2 of tau, all the way to the last location, the qth location, IQ of tau. And verifier evaluates whether to answer yes or no. So the verifier, for example, could use the 3 sat predicate. He read 3 bits sitting inside a clause, and now he wants to like return whether this clause evaluated to true or false on that assignment. So, and the verifier evaluates some predicate C sub tau, where C sub tau is a predicate sitting on these q locations, and it outputs either an accept or a reject. That finishes this bulky part. I'm aware that this part is bulky, but then again, like let's make sure that we understand what's going on. So we are already aware that there is this deterministic view over here of the class NP, right, which is pretty straightforward, something that you are like used to. You already know that like you know, for a problem in the class NP, verifying membership is easy given a certificate. Verification of certificates is easy. I claim that this graph has a clique of size 100. I give you those 100 vertices that I believe in induce a clique. You can just go and check it. Right? So that's the classic view. I'm saying that in this view, if you allow verifier the liberty to toss coins, something miraculous happens. And what is that miracle? That you can check proofs by just flipping onto a random page, checking at a random line. Right? That's all this entire setup is just saying. And what we are resorting is that view 1 and view 2, they are identical. Okay. Any questions about view 1 and view 2? The fact that they are identical is yet to be shown. Any questions?
Are we querying these locations?
Good. So you toss your log and random coins, alright? So let's suppose that my number of random coins that I have is in fact 30 times log n. So let's suppose that the size of tau is 30 log n. What I can imagine doing is that I break this chunk of 30 log n into 10, into like 3 bit sequences, I will call them bit sequences, maybe B1, B2 and B3, where size of each BI is 10 log n, right? So what this 10 log n arrangement of bits allows me to think about is that it allows me to index into a proof of size n power 10. So I go and look up this fictional proof of size n power 10 and I read 3 bits in there. The first bit is indexed by B1, the other bits are indexed by B2 and the last bit is indexed by B3. Right? So B1, B2, B3 become indices inside my proof. I interpret the sequence of bits B1 as an index into my proof I1 of tau. I interpret the bit sequence B2 as an index into my proof I2 of tau. I interpret the bit sequence B3 as an index into my proof I3 of tau. So I query these 3 bits. I evaluate some predicate there. My predicate might be that all bits are identical. Alright? So for instance, that will be my predicate. And then I accept or reject. Okay?
So the indices we are checking is the size of B1.
So size of B1, so B1 is a collection of 10 log n random bits. Right? So 10 log n random, so imagine that the proof pi looks like the following. So this is my proof pi. Here is like maybe location 1, location 2, location 3, location I, up to location n power 10. So the bit sequence B1 can index one of these locations. That's all I'm saying. That B1 indexes one of those locations, B2 indexes another one, B3 indexes another one. I look at these 3 bits and then I just like evaluate some predicate over there.
So a certificate in the original NP view, can that be converted to one?
Yes, we will go there slowly. So you are already trying to think how to show the equivalence between these 2 views. Okay? More questions about the setup. The setup is bulky. Yeah, the proof pi is polynomial in size. The proof pi has poly size. So, yeah, more questions?
So
So n
n is length of x.
is the length of the instance. The size of the proof is poly.
This string is the instance, right? X.
So x is my instance. X is my instance. Yes. So x is like the instance of 3 sat, and that's bad notation. Who calls 3 sat instance x? Sorry. I don't know. I mean that's on me. So yeah. Okay. So now I will show the equivalence of these 2 views. Yeah, so the annoying thing about PCB theorem is that there is this very cool advertisement, but then in order to make sure that you understand the punchline of this cool advertisement down all the way mathematically, like I mean that's a fairly intricate and intense setup, and like this is the least of it. If you think that like this is bulky, like there is a lot more to come. By the way, Professor Prasad Harsha taught an entire like class on PCB theorem. And like the video of that like lecture series is available. You should definitely take a look if this thing intrigues you. Okay, so the first claim that I am going to make is that view 1 implies the other view. View 1 implies view 2. What does that mean? What am I required to show? Somehow I am supposed to convert the inapproximability view, seems like a very combinatorial thing, into this verification view. Right? I'm supposed to go from here to here. I get to assume that gap 3 sat is hard. Right? That's what I get to assume, gap 3 sat is hard. And I want to somehow end up in this proof verification view. Any ideas how can I do it? It's not very hard. I get to believe this, gap 3 sat is hard, and like gap 3 sat is NP hard because it reduces in polynomial time, so gap 3 sat belongs to NP. Can you say something now? So maybe I will like start writing a few things. Call your gap 3 sat instance maybe Psi is better. So what we are going to do is we are going to start a dialogue. We are going to start a dialogue between verifier and the prover. We are the verifier, somebody else is the prover, that person is a liar. His entire job in his life is to convince us that some gap theory set instance is in fact satisfiable. If the gap theory set instance were truly satisfiable, this guy is in great luck. He can just output a legitimate proof. But if the gap theory set instance is not satisfiable, or just remove it, then this guy will lie through his teeth. We are supposed to catch him. Yes, question.
So I think that the probabilistic protocol would be that if the gap tree set is true, like if it is no instance, then there are some clause that are unsatisfiable.
Good, you got it.
We have to.
You got it. I should have brought chocolates. That's a chocolate question. Good, you got it. That's it. But let me. So what's your name? Devmal. Okay. Later. I'm sorry. Yeah. So here is how the proof is going to work. You're the verifier. I'm going to call you Dev. Is that okay? Or did I get your name completely wrong?
Okay. It's Dev Malya Hazra.
Dev Malya. Okay. Good. So we have Dev Malya here, right? He's the verifier, and here we have our prover. So I even made those cartoon pictures in my notes because I like thinking in terms of these cartoons. So the verifier says, I have an instance psi. This guy responds, okay, sure. Now the conversation begins. Right? So he says that, sends over the instance psi and then issues a challenge. Open challenge, all right? So he's pretty brave. Okay, so that's Dave. So give an assignment to variables in psi, right? To a random clause. So Dev Malya chooses a clause at random and challenges the prover. Can you give me an assignment that satisfies this clause? Okay, so the prover has to respond with an assignment. The prover has to respond with an entire gigantic assignment, pi, right? Claimed proof. Reminder, it could be bogus proof. Okay? And now, like the rest of the life is pretty easy. They can just go and check a random clause and they can check whether this assignment is good or bad. That's all. Right? There is something that might be unsettling for you. It's not too unsettling though. I mean, for instance, what you might end up encountering is that the probability of rejection is only 1 minus alpha, or the probability that a bogus proof gets accepted is at most alpha. But you can always boost it. You can always boost the probability by just mere repetition. Right? So that takes care of how you can go from U1 to U2. Okay. Now let's see how you can come back. Let's see how you can come back. U2 to U1. So this is a pretty easy proof. I mean, you just set up a dialogue, right? And in that dialogue, I'm going to exploit the fact that there is a gap. That my 3-sort instance, whenever it's falsifiable, it's not just falsifiable, it's royally falsifiable. Alright. So the probability that I was unlucky enough to land on a clause that your stupid assignment knew how to satisfy was at most alpha. So in a single round I will get fooled, मैं उल्लू बनूंगा with probability at most alpha. So if I just repeat it enough times, I can bring the probability further down. So that's the entire argument. So now let's see if U2 implies V1. This has one interesting idea that the people in PCB literature love. I'm sorry, I am a bit over time.
It's fine. We started 15 minutes late, so you have another 10-12 minutes.
Okay, good. Yeah, thank you. So V2 implies V1, that's what I would like to show. So the key idea here, so again, what do you want to show now? For any language LNP, I have this PCP system using R queries, using R units of randomness and Q queries. I have this PCB system. And somehow I am being given the task, the annoying task of coming up with a reduction that takes me from 3 set to gap 3 set. Okay, what do I do? Alright, so the key insight is something like this, that here is my instance X of some language L in NP. So I have some language L in NP, right? I can choose that language to be 3 sat. So I choose the language L to be, so maybe I should start there. That. And take some instance X. And let's not, so pretend that you are given the proof but you don't really see the proof. Okay, verifier does not really see the proof. So that's one convenient way to think about the intuition for this argument. So here is some proof pi. So I'm going to pretend I'm the verifier. I do not get to see the proof, but I know that when I tossed by random, so this proof pi could have been a bogus proof, it could have been a legitimate proof, I do not know. This proof pi is something that the prover just produces, maybe out of thin air. It's probably some bullshit or something, I don't care. So I look at this mysterious proof pi, possibly a fake proof, which I did not even know. I know that this proof pi has size, let's say, into the 10. Okay. So I toss my random coins. I pretend that I do not see this proof. I only care about one thing, that if my random coins, if all the tosses came out a certain way, which locations am I going to query? That's the only thing I care about. I only care about which locations I am going to query. Those locations could contain garbage. For example, I query locations I, locations j, locations k. Maybe they contain 000, maybe they contain 101 or some other bit pattern. I don't care about that. I only care about which locations is it that I am looking at. Okay. So here is my verifier V, and as I said that the key idea is to pretend that the verifier does not see the fake proof. Okay. So we would like to have the verifier come up, in a somewhat imprecise sense, come up with the proof pi on his own. Okay, so this will finally help you produce this polynomial time reduction from 3 set to gap 3 set, as you will see. So what happens is that the verifier thinks the proof pi is some unknown sequence of bits. I again emphasize this is unknown. That's what the verifier is actually pretending. So the idea is that while the verifier does not know what this unknown proof pi actually looks like, or is pretending he does not know what this proof pi looks like, verifier does know what indices he is going to query on a certain outcome of the random coins. So the verifier does know for every tau in 0, 1 to the number of random coins is allowed, right, or 0 to the tau, 0 to the r, 0 to the r, what locations to inspect. So for example, locations that are inspected on a particular tau are I1 tau, I2 tau, all the way up to IQ tau. These are the Q locations that you inspect. That's it. Okay, so now what the verifier can do is that verifier can start building some constraints. So it's kind of like you have a graph or a hypergraph, a Q-uniform hypergraph if you will, and all the verifier is now trying to do is he's trying to look at this Q-uniform hypergraph, and the verifier is trying to think how many constraints, how many hyperedges of this Q-uniform hypergraph can an assignment satisfy. The entire intuition is that all assignments falsify half fractions something here, so a lot of things should be broken here. A lot of these Q tuples are going to be broken no matter what kind of hypergraph you produce. Right? So that's the entire idea. Right? It's again a pretty simple idea at its heart, The idea is to just use the gap here between 1 and 1/2, right, to produce a reduction where you have q tuples. It's not a 3-sat instance, right? So I did not quite produce a 3-sat instance, but I produced something which is like still better than nothing. So I produced a q-uniform hypergraph where the number of constraints is actually poly n. Number of constraints is poly n because, like, you know, R, the number of random bits, is just logarithmic. Right? So number of constraints is poly n. Each constraint is a q-uniform hyperedge, right? And at least half of those edges get broken no matter what assignment you try. Okay? So the value of this instance, value of the instance after reduction is actually 1/2. But now you realize that, you know, this is like our classic problem from Mike Sipser, that you are given some NP-hard problem, right? So this q-uniform hypergraph that you end up with, like, is in fact something that you obtained from the 3-sat instance in polynomial time. So whatever this instance is, whatever decision problem on q-uniform hypergraph is, it's an NP-complete instance. But I always know how to go from an NP-complete problem, which involves q variables, to an NP-complete problem that involves 3 variables. In particular, we know how to go back to the 3-sat instance. It's just that my value would go down. Here, like, you know, the no instance had a very small value. The value was at most 1/2. My value would possibly become closer to 1, but I would still have some gap as a function of q. So the idea now is to go from this q uniform hypergraph down to 3-sat where the value of this 3-sat instance, I'm going to call it phi, in the no case, would be at most, like, you know, something like that. So, like, that's something that I'm not going to prove because it's a standard thing that, like, you know how to do thanks to the complexity chapter from Mike Sipser. But this is pretty much the entire argument, that these two views are in fact identical, right? And the proof was actually not that difficult for both of these cases, right? The proof for view 1 implying view 2 was in fact a fairly direct proof. And this proof is also not that bad. I mean, you first argue hardness of some fictional problem on q-uniform hypergraphs, and then you show that you can go from this fictional problem down to 3-sat. Perhaps it's a blow up in the, like, value. Alright? So there is a lot more to say here, but like, you know, there is not enough time. But like, the lecture notes that you have also say, like, a few additional things about how you can show hardness result for the maths clique problem. So we are welcome to look at that, but I guess with that I'll stop. Questions?
This is pretty much your last chance to ask questions during the summer school, so.
How did we construct the q-uniform hypergraph?
Good. So, like, the entire idea was that, like, you know, I look at these q locations that I know I'm going to inspect. So I fix some tau. Okay, this is a collection of log n bits. So every collection of these, like, big O log n random bits specifies q locations of fruit that you're going to inspect. I don't care what's written in those q locations. Alright? So these q locations are going to receive some assignment, some 0-1 assignment, right? I'm just going to add these q locations, this q tuple, as a q uniform hyperedge in some hypergraph that I'm building piece by piece. So I obtain one hyperedge for every tau. I obtain an hyperedge for every tau. Okay. And then like, it just becomes a labeling problem of this q uniform hypergraph. Is there a good labeling? Is there no such good labeling? Okay.
What corresponds to a good labeling?
So what corresponds to a good labeling is a satisfying proof. If I have a proof that satisfies all the q tuples that I can potentially inspect, then you can stitch together, right? I mean, those proof and everything is consistent. Yeah, I mean, the literature on this can be a bit overwhelming. Like, so my suggestion to all of you would be to, like, go and look up Professor Prahlad Harasha's video reviews. They're fabulous.
Any other questions? Okay, if not, let's thank the speaker.
So I'd like to say a few things. So I mean, like, thanks a lot to the organizers, Arka, Ritabroto, like many other people, Parag. So, like, thanks for organizing this summer school, like, lot of effort. So let's thank all the organizers.